In this final video, we're going to look at examples 13, 14, 15, 16 of the 5.2 worksheet with verifying trig identities and hopefully strengthen our understanding of the concepts behind it. If we look at problem 13, I'm going to keep the left side. To me, this is the simpler side. It's the product of secant of x and cosecant of x. And the reason why, my justification for keeping the left side is because they are, in a way, what we would call previously like terms. Secant is 1 over cosine of x. Cosecant is 1 over sine of x. And so there are already, in a way, hidden types of forms of sines and cosines. So that's why I'm leaning towards keeping the left-hand side. And I'm going to keep this up here. Because if you think about it, that's going to create my side. So there we go. I kind of know what my second to last step on this right-hand side is going to be. So if I take a look, that means I want to create sines and cosines. So tangent of x is sine of x over cosine of x plus cotangent of x, which cotangent of x is cosine of x over sine of x. So where do I go from here? Well, we see a common theme that's repeating is I have a fraction and I'm adding another fraction. So my mind's telling me I'm going to want to combine those together by finding a common denominator for it. So I have my left side, secant of x times cosine of x, cosecant of x, equals, well, I need a common denominator. So what am I going to do? Well, I have sine of x over cosine of x, and I have the reciprocal cosine of x over sine of x. I'm going to put a sine of x in the denominator of the first fraction, so I need to put it in the top. And I'm going to put the cosine of x in the denominator of the second fraction, and I'm going to put it in the top. So that's the theme of common denominator. And why do we create a common denominator? So we can merge them together into a single fraction. So my left side stays. I'm going to remove the red line, just to keep going. And hopefully you know that means you can't cross it. Now I can merge them into one fraction where it's going to be on the bottom, cosine of x times sine of x. Well, what's it going to be on the top? We have sine times sine. And so that's going to give me sine squared of x plus we have cosine times cosine. And so that's going to give me cosine squared of x. So again, the common theme, we have two fractions that are being added together. So I want to create a common denominator, and then I'm going to merge them into a single fraction. Well, again, where do I go from here? Well, the left side, we're staying secant of x times cosecant of x. Well, the right side, there's a couple interesting things. I see a squared trig ratio plus another squared trig ratio. Now, that's not a 100% guarantee, but that is something that tells me that could be a Pythagorean identity. Well, sine squared plus cosine squared is 1. And what's very interesting on the denominator is I have a cosine of x and a sine of x in the denominator. If I go back to the top, that's what I wanted. I wanted to have a cosine of x and a sine of x in the denominator. So I notice I'm getting really close to what I wanted. Well, in this case, if you have a cosine of x in the denominator, you really have a secant of x. And if you have a sine of x in the denominator, you really have a cosecant of x. And therefore, the left-hand side equals the right-hand side, Q, E, D. It has been demonstrated that the secant of x times cosecant of x equals tangent of x plus cotangent of x. So in this case, again, hopefully you're starting to get the idea of themes do repeat. You're adding or subtracting two fractions, you want to find a common denominator and merge them together. If you have squared trig ratios, that should get your mind starting to think I should look for Pythagorean identities on it. All right, so let's take a look at 14. Now 14 is a little bit tricky when it comes to the concepts behind it. And if I look at 14, what I want to do is I want to look at which side is the one I'm going to keep and which side is the one I'm going to change. Now, in my opinion, for 14, I am going to keep the right side. I am going to keep the 2 sine squared of x minus 1 over sine of x minus cosine of x. And you may wonder why. What's telling me to keep the right side but to change the left side? And the reason why is right in the beginning, and I'm going to kind of do this. The right side's a fraction, so let me just show the left side as a fraction as well. And by doing that, I can see there's something interesting. This has a sine of x plus cosine of x, and this in the denominator, the opposite side of the fraction, has a sine of x minus a cosine of x. So just like in a previous video, that tells me I have the same terms but the opposite operations. And so when I see this, my mind starts going to the idea of conjugates. They're related that way to each other. So what I'm going to do is I am going to multiply the left side by a clever form of 1 using the conjugates. The conjugate is sine of x minus cosine of x. So I'm going to put that at the top, and I'm going to put that in the bottom. Why is it interesting is because, let me just put this over 1 so you can kind of see you're multiplying 2 fractions. It's allowing me to visually see how do I get my mind wrapped around conjugates is I can see it in the beginning from them. So that kind of gives me an idea of what my step's going to be. And what's good about it is I want a sine of x minus cosine of x in the bottom, and I now created it right in the first step, which tells me I'm not going to change this denominator. I'm going to keep it because I want it. So let's not add to it. Let's not multiply into it. Let's just keep that as is. But on the top, what do? I want a sine squared. So I'm going to multiply my numerators together because that's going to give me sine of x times sine of x, which in fact gives me a sine squared of x. I'm going to have a sine of x times the negative cosine of x. So sine of x times negative cosine of x. And then you're going to have one that's positive. And then cosine times negative cosine is a negative cosine squared of x. Now, I did the full distributing here, which is actually the first time I've done that with the conjugates. Really, what I've done before is I've used the idea of conjugates are the same terms in the opposite operation, which is the factored form of difference of squares. So really, I could have just squared the first term and squared the last term. And that would allow me to get the same thing, because if I look at it, I will see that the other ones cancel out for it. And I believe I did forget sine of x here for it. So I like to use, when I'm doing conjugates, we'll fix it and just say it's the first term squared minus the second term squared. So I get sine squared of x minus cosine squared of x over sine of x minus cosine of x. Let me get rid of this since I know which side I'm keeping and which side I'm changing. So the right side stays the same. Again, I'm not going to in any way change the denominator on the other side because it's perfect. But there's a problem, is the top isn't right. I want 2 sine squareds. I only have 1 over here. I have 0 cosines on the right side, but yet I have a cosine squared here. And that's where we have a mistake, is I have a cosine squared. On the right side, I have a number 1. So just like in a previous problem, as a really more complicated problem that we did, is I am going to use the reverse of a Pythagorean identity. I am going to change cosine squared of x into 1 minus sine squared of x. And because it's an object, I'm going to put it in a parentheses, and I'm going to keep that sine squared of x on the left. Keep my denominator. And let's see what happens. Equals the right hand side, 2 sine squared of x minus 1 over sine of x minus cosine of x. Well, I distribute top. So I'm going to have sine squared of x minus 1 plus sine squared of x over sine of x minus cosine of x equals that right-hand side. So now what's nice is by using that reverse of Pythagorean identity, I'm able to create all sine squareds. So how do I know to use the reverse of Pythagorean identity is because sine squareds and cosine squareds are related that way. And if I don't want cosines and I only want sines, I'm going to rewrite it with those terms. So sine squared plus sine squared plus sine squared gives me 2 sine squared of x minus 1 over the denominator that stayed the same for a while, sine of x minus cosine of x. And lo and behold, that is the right-hand side. So it has been proven. So this is the second time we have used the reverse of a Pythagorean identity. And you want to get used to the format of it. Like why? When do you use it? And it's because I have sine squareds and I want sine squareds, but I got a cosine squared here and I don't want a cosine squared. I need it in terms of sine. And when that happens, that's when you use the reverse Pythagorean identity, is when you're guaranteed you can only have sines on top. And you have a cosine on the right side that's squared. You want to use Pythagorean identity so that you can create the exact same trig ratios. Very hard concept. This, like I said, this is the second example that's done it. Just kind of get used to that idea. Let's take a look here for number 15. When we're looking at number 15, what we're going to want to do is figure out how to go about the process. Now, in this case, I am going to work on both sides just to kind of get some practice with it and with simplifying along the way. So when I work on both sides, just separate it visually in the beginning to kind of help me out. To square something means to multiply by itself. And so that's what I'm going to do. I am going to write sine of x plus cosine of x times sine of x plus cosine of x. And let me just keep going on this right-hand side. And I'm going to kind of slide this down because the lines need to line up on the left and the right. So when I start simplifying the right side, we have it there. Well, now I'm going to distribute. And when I distribute, I'm going to get sine of x to sine of x. And so that gives me sine squared of x. Sine of x to cosine of x, so plus sine of x cosine of x. And then I'm going to distribute the cosine of x. So that cosine times sine would be sine of x times cosine of x. Cosine times cosine would be plus cosine squared of x. And I managed to make it fit in that area. Well, that's a lot. So let's figure out what we're going to do. If I were to take a look at this, it's all addition. And what stands out to me is I have a sine squared over here, sine squared of x, and I have a plus cosine squared of x. That is a Pythagorean identity. Using the commutative property, I can actually combine them together. Sine squared plus cosine squared is 1. And the middle terms are the exact same. So really, it's like saying I have plus 2 sine of x cosine of x. And so let's see what happens on the right-hand side for this. Because I can't combine any further, so I'm going to leave that and just kind of start going through the process. Again, let me just kind of drag this down, give myself some more room to work with. All right, what about the right side? Well, look at it. It's secants and cosecants and secants and cosecants. That's not fun. So what I'm going to do is I'm going to change them a little bit and mess around with it. One really interesting thing that I want to do is I want to break apart this fraction. Because I notice I have a 2 here. And I have a 2 here. And I have a plus sign. So I have 2 terms on the left side. But right now, I really have only one fraction on the right side. But if I can split it apart, and we did this in the previous problem. So notice the last 4 start to take these new concepts in the beginning problems and start to apply them. Is I'm going to split the numerator. So I'm going to write 2 over secant x times cosecant of x plus secant of x times cosecant of x over secant of x times cosecant of x. Well, I wrote cosine both those times. Now, why is that helpful is I can see I'm getting the 2, and what's really interesting is I can look at this over here. And so let me get rid of some of the highlighting in this step. I can see right here I have secant of x times cosecant of x over secant of x times cosecant of x. Well, anything divided by itself is 1. So I can start to see why did I split this apart. Is I could see little structures that are similar to what I have, but yet I didn't have the denominator. I wanted to split it apart on it. So I'm going to do that. And it's going to be interesting what happens is because anything divided by itself is 1. And you can even use the idea that this entire term is all multiplication, so I can cross out common factors in the top and bottom. So there's that theme again. So I have a plus 1 in this step. Well, on the left side, I have sines and cosines. On the right side, I have secants and cosecants, which aren't going to work. So I'm going to do this, 2 over 1 over cosine of x times 1 over sine of x. So that plus 1 is simple. And again, notice I have it over here, I have it over here. I am so not changing it. I have part of it to work. I have a 2 right here. I have a 2 right here. I am so not changing that because it is exactly what I need. But what I am going to change is the denominator. Now, I'm going to flip and multiply. So I'm going to keep the 2 over 1. So I'm going to keep this numerator. I'm going to flip this denominator and multiply. So cosine of x and sine of x go to the top, and 1 goes to the bottom. Well, look at that. So right now, the left-hand side is 1 plus 2 sine of x cosine of x. And I'll write this down as just the way it appears, 2 cosine of x sine of x plus 1. So the left-hand side visually is not the same as the right-hand side, but mathematically they are equal to each other. And because addition is commutative, so I can move the positive 1 over to the left. My plus 2 sine x cosine of x, I can move that to the right, and multiplication is commutative. So I can put the sine x first, and then the cosine x in there. It is exactly the same, Q, E, D, done. And that's all the steps. Not something that's new, something we did in a previous problem for us. It's something that's interesting that we are again splitting a fraction apart from the first step to the second step. And you gotta get used to when does that happen. Now, one other interesting thing that we could do and look at is the idea that if you have secants and cosecants in the denominator, those are part of our reciprocal identities. Is if I have a secant and a cosecant in the denominator, I'll just put over here, and I put equals, I can actually realize that means I have a cosine and a sine in the numerator. So I can write it up top and put the original in a parentheses. And then if I distribute, I would get 2 cosine of x sine of x. And when I distribute here, the cosine and secant are reciprocals, and the sine and cosecant are reciprocals. And so look at that. I go right from the beginning to, I'll write down LHS for left-hand side, right to the 2 cosine of x. I mean, right here. Look at all the steps I skip by applying my reciprocal identity. So there are multiple ways of doing the problems. It's the idea of what comes to your mind. And this approach I did was, I'd say, a basic approach of going to sines, cosines, and figuring out what to do. But if I can realize my reciprocal identities, it's actually a faster approach to do that problem. So something interesting to kind of know and see that there are some new ways to kind of expand your understanding of trig identities if you get really good at them. So the last one's number 16. Well, if I'm looking at number 16, something just tells me that means I'm going to keep the right-hand side. I mean, that's just a simple negative cosine of x. Really can't create anything like that. So what am I going to do to the left side? Well, you can distribute. That's one way of doing it. We could realize that this is not a Pythagorean identity because there's no squared there. This is not a Pythagorean identity because there's no squared, so I'm not leaning towards Pythagorean identities. What I'm going to do is I'm going to go ahead and work with, because we need some time, I'm going to distribute and then go to fractions. So sine of x times tangent of x plus sine of x times secant of x minus tangent of x minus secant of x. Don't worry, I will create the room I need. And so there we are. And that is a lot. 4 terms. Shrunk down a little too much. There we go. And we're just going to work with them separately. Is I have a cosine here. I do have some sines, and that's nice. Then I have a tangent, a secant, a tangent, a secant. They're not like terms. And again, like terms means I probably want to convert to sine cosine. So for the first one, sine of x times tangent of x, it's sine of x times sine of x over cosine of x. And if it makes you feel better to put this over 1, you can. Plus sine of x times secant of x. So I'll put sine of x over 1, and then secant of x is 1 over cosine of x, minus tangent of x. So minus sine of x over cosine of x. And then minus secant of x. So minus 1 over cosine of x. Again, this is a lot of fractions. I'm doing it this way first because I want us to get used to the idea of fractions and combining them. You need common denominators. It's that theme. Let's do this first. Sine times sine is sine squared. So I have sine squared of x over cosine of x. And then what I have is I have sine of x times 1 over 1 times cosine. So plus sine of x over cosine of x. I have minus sine of x over cosine of x, the purple one, can just drop down, minus 1 over cosine of x. So I have common denominators between all of them. And I'm also going to notice is these are the same except for opposite operations. So those are going to cancel out when I combine them together. So let's merge them into one fraction. And I have sine squared of x minus 1 equal over cosine of x equals negative cosine of x. Again, I want cosines. And unfortunately, I have a sine squared. So when that happens, my mind goes to the reverse of a Pythagorean identity. Is can I change sine squareds into cosine squareds? And I can. Sine squared is 1 minus cosine squared of x. And I have the minus 1 over cosine of x equals negative cosine of x. Well, 1 minus 1 cancels. So I have negative cosine squared of x over cosine of x. And in this case, I can use my properties of exponents and realize I can cancel out one of the cosines on the top with one at the bottom. And that gives me negative cosine of x equals negative cosine of x. QED, it has been demonstrated. That is a long one. And that is I would say, one of the most basic approach, notice I didn't say simplest, it's the most basic, going to sines and cosines. Distributed. And by the way, notice I distributed and went to sines, cosines. That was a little bit easier for it. At least easier in this case to see the four terms. But there's another way to do this problem. And because I enjoy trig identities so much, we are going to look at the other way as well. So let's just take this, shrink it down, and I'm going to do something that I kind of criticized before, which is I am going to change to sines and cosines in the beginning. And why? Just because I can. And you don't learn any interesting things unless you try it. So I like the first one. And I'm going to change this to sine of x over cosine of x plus 1 over cosine of x. So why change equals negative cosine of x beginning? Because I notice that they already have a common denominator here. So I have sine of x minus 1 times a fraction, sine of x plus 1 over cosine of x equals negative cosine of x. Well, if I take a look, this is really over 1, and I'm going to remove this parentheses now, and I'll just put it on the top, because that's the one with two terms. If I take a look there, I can distribute, and I'm not going to distribute all of it. I'm going to take a look and see that these are conjugates of each other. They are the same terms, the opposite operations, which is the idea behind difference of squares. And so I'm going to square the first term and subtract the square of the second term. And then on the bottom, 1 times cosine is cosine. And why? I'm not going to finish the problem. And the reason why is because I already did previously. Notice I got right to that step. And then I would use the version back like I did to go through the process. So they start to get the same. And notice it didn't really save me too many steps. I mean, I get 1, 2, 3, and then the fourth step I got to here. Here I had 1, 2, 3, and I got there. So it saved me one step in the grand scheme of things. But to me, the left side looks nicer because I don't have as many fractions dealing with it. But I have to be comfortable with working with fractions. I have to be comfortable with doing it in the middle of work and then combining. So my algebra skills have to be pretty good. So that's 13 through 16. Hopefully this series of videos helped explain and help you understand how to verify trig identities.